Hello friends, welcome to another video. In this video, we are going to implement the UNet architecture in PyTorch framework. So this is going to be my first video on the PyTorch framework. I'm really excited. I hope you're also excited. And please make sure that you like the video and subscribe the channel. So without any further delay, let's start the video. Here you can take a look at the original block diagram for the UNet architecture. So it's an encoder decoder architecture. So you can see on the left side we have the encoder network, or we can also call it the contracting path, and on the right side we have the decoder network. We can also call it the expensive path. So basically contracting path and expensive path terms are used in this paper. Okay, so you can see the encoder takes the input image in a it can be an RGB image or a grayscale image on any other image, and it passes through the encoder, then goes to the decoder, and the decoder outputs the segmentation mask. Okay, and in between we can see there are skip connection connecting the encoder to the decoder at various level. So there are 4 different levels, so 4 different skip connection are there. So these skip connection help in direct propagation of information from encoder to decoder. This information can be sometimes lost due to the depth. If you see the information from the first encoder block, it goes to the last decoder block through various convolution and batch normalization and different layers. But if we use skip connection, it directly passes. So this is one of the major advantages UNet, that the direct propagation of information through skip connection. And we can also see that during the back propagation, as when the everything flows from output to the input layer. Okay, and these skip connection help in direct propagation of gradients. Without this skip connection, the earlier layer won't won't receive much of the gradient value. So this is basically, these skip connection are really useful. Okay, so now let's move to the area where we have the network architecture. Okay, so we're going to read this, study this, and try to implement the UNet architecture in the PyTorch framework. Okay, so let's read it from there. The network architecture illustrated in figure 1, it consists of contracting, the left side, and expansive path, the right side. Okay, that we have discussed. The contracting path follows a typical architecture of convolutional network. Okay, now the main thing comes. It consists of repeated application of 2 3x3 convolution. Okay, here it is written unpadded, but for our video demo purpose, we are going to use the padded convolution for the easiness, and each followed by a ReLU activation. Okay, so they have the convolution layer followed by ReLU, but between these two layers we are going to introduce the batch normalization also, and a 2x2 max pooling operation with a stride of 2 for the downsampling. So to decrease the size of the height and width of the feature map, we use downsampling. So this is all about the encoder. So now we have seen the encoder thing. Now let's start to program it. After that we move to the decoder part. So first of all, we are going to import the libraries, that is Torch. Okay, so we have imported the library. So first of all, let's move the paper, and here you can see it has shown that it typically it consists of repeated application of 2 3x3 convolution, each followed by ReLU. So we're going to first create a simple module with 2 3x3 convolution, and each convolution is followed by batch normalization and then a ReLU, and giving the output of the second ReLU. Okay, so let's class, you can say con block. Okay, so we're going to call this con block. Okay, so this is a child class of this base class. Okay, and inside it we're going to define the constructor init, and inside the constructor we're going to take some parameter. So first is the number of input channel. So we are going to receive a input feature. So how many feature channel this input has is denoted by the in_c, and how many output features we want, and this is going to be denoted by outc. Okay, okay, now here in the constructor we need to define the layers first. So define the convolution layer first. You can also go to the PyTorch documentation to learn more about these layers and their parameter, what they do. So first of all, it take the number of input channels, then the number of output channels. Okay, the third is the kernel size. So kernel size is basically a 3 by 3 kernel, so we're going to say 3. So writing a single integer basically means we are using a symmetrical kernel. So if you want to use like 2 by 1, so you can specify 2 by 1, but we want to use it 3 by 3, so you're going to simply write 3. And we are using its padding, so we're going to say 1 here. So padding is 1. Like in TensorFlow, here padding value should be same. Okay, now the next is the Bayes normalization. Okay, B should be capital. So it's batch norm 2D, and it take the number of output features. Okay, basically it take the what is the input it takes the number of input channels it receive as the input. This layer would receive an input. The output of the convolution layer act as the input for the Bayes normalization layer. So the number of output channel in this layer would be out C. Okay, the next is a ReLU. So we're going to define a ReLU. ReLU is basically not a learnable parameter, so we're going to define it alone here, and we can use it anytime we want. Okay, so let's do this first layer first, these 3 layers first. So we're going to say forward. So in PyTorch, this forward basically receives the input feature. We're going to say inputs, not X, because you also know that the inputs basically denote the input feature map. So we're going to say X equals to, now we have defined this layer, we're going to use this layer. Let's say X is equals to con1 and input would be inputs. So let me just show you what happens and what thing are going behind the scene. Main. So okay, first of all we need an input tensor or an input feature map. So we can say inputs dot rand, and okay, here you need to specify shape. So if you come from TensorFlow and you are new to PyTorch, so there's one major change here. In TensorFlow, our shape is just like, I will show you batch size, then we have height, then we have width, and then we have number of channels. But in PyTorch, it just changes to, first we have batch size, then we have number of channels, then we have height, and then we have width. So basically the axis for the number of channel would changes from the last to second. Okay, so that is the major change we have here in the PyTorch. So we're going to say batch size is, let's say 2, number of input feature is 3, and height is, let's say 512. Okay, so we're going to call this con block C, con block, and okay, so the number of input would be 3, let's say number of output channel would be 64. So we're going to give input to C, the inputs. Okay, now I'm going to print the shape for X inside the forward function. Okay, so let me activate my virtual environment. Okay, let's see. Okay, so you can see the output of the convolution block is like it's have different number of output channels, as we have specified 64 here. So the height and width remains the same, the base remains the same, just the number of channel differs. Okay, now we're going to apply the Bayes normalization layer. We're going to say X, and then we're going to apply the ReLU. Okay, now let's check its shape, if it remains the same or there is any major change. So you can see it remains the same because the Bayes normalization and ReLU don't add anything, just work on their own. Bayes normalization is still a learnable thing, but the ReLU is not learnable actually. It's just activation function. It's a non-linear activation function basically. Now we're going to again have these layers, because as the paper says there are 2 3 by 3 convolution each followed by ReLU. So here the input would be changed. Okay, we have to specify these layers also and above. Okay, so let's first do these layers. We're going to say con 2 batch normalization 2. So here you can see, let's do this. So we need to make proper changes. So here the x, we have this x. Okay, so here we need to provide the input number of input channel. So the output of the ReLU, the output of the ReLU has 64 number of channel. So we're going to say out C. Okay, so don't say in C. Okay, in C basically refers to number of channels in the initial input. Okay, not the output of the ReLU. So here's out C and out C, basically 64 input channel and 64 as output channel. Kernel size 3, padding 1, batch normalization, and then followed by ReLU. Okay, so this sequence works. Let's run it again. Okay, you can see we have again same shape. Now we're going to return this x. Okay, so we are done with this convolution block. Now we're going to work with the encoder block. Let's say encoder block. Again we have this nn.module class called here. It's a base class and we are creating a child class for it. Constructor self number of input channels, number of output channels, and then done. Okay, so encoder block is basically the convolution block followed by the 2x2 max pooling. So let's call the con block here. We're gonna say convolution block. It take a number of input channel, number of output channel as the two parameters, and next we have the max pooling. So we're gonna say pool and nn.max pool pooling, and inside it we're gonna say 2x2. Okay, so the layers are done. Now we're gonna work on the forward function, which takes the input feature map. So we're gonna call it inputs. Now let's say x equals to self dot conv inputs. The next is the pooling. So we're going to say x. Okay, so here you have x, the output of the convolution block, and which act as input for the pooling layer. So here the x also act as a skip connection, and p act as the input for the next encoder or the decoder block where it is placed. So we're going to return both the things, x and p. Okay, now we're going to work with this x and p. Let me remove this. So we're going to say e as the encoder block. So input is 3, output is 64. Now we're going to say x and p equals to e inputs. Now we're going to print the shape and check, because if you are working with deep learning and layers, you need to exactly know what shape is there. You need to already predict them in mind. That's how a thing works much better way. So you can see the shape of the x, or basic the skip connection of the output of the convolution block, remains the same. The height and width remain the same, and the number of channels is 64. But in case of pooling, we can see the height and width are decreased by 2. Okay, and number of channels remains the same. So that's how the rest of the encoder block also work. This subsequently reduce the height and width and increase the number of channels. Okay, so encoder block is also ready. Now let's read the next part and work with the decoder part. Okay, so where we are, okay, here at each downsampling step we doubles the feature channels. Every step the expensive path consists of an upsampling of the feature map followed by 2x2 convolution, or we can say up convolution, or the transpose convolution that halves the number of feature channel. Okay, so till now what it says, at each step, basically at each decoder network, at every step of expensive path, the upsampling of the feature map. So first is followed by 2x2 transpose convolution. So let's do that. We're gonna go slowly one by one. Okay, again we're gonna build a module called decoder block. So again that class, the base class, again the in constructor. So if by mistake I've called it the instructor, it's basically the constructor of a class. Okay, so again the number of input channel and the number of output channel. So first we have the transpose convolution. Before that, let's try this super function. Okay, so let's define this up convolution or the transpose convolution. Transpose con 2D. So first it take number of input channels which we have specified, the number of output channels, kernel size. Okay, there should be comma here. Kernel size is 2 as mentioned in the paper. Stride is going to be 2 because we want to double the height and width basically, and padding would be 0. Okay, now let's go to this forward function. So here we have two inputs. First is the previous layer output, and second is the skip connection. Okay, as you remember in the diagram we have seen, let me just show you again. So here you can see, like, this is a decoder block here. These are the layers for the decoder block. It received this in output of the previous layer, and also second input is the skip connection. Okay, so these two we receive. Okay, now let's simply run this part only. First let's do x is equals to self dot up, and we're going to say inputs here. Okay, so I'm going to do two things. We're going to print the three shape. First is inputs. What is the shape of input? Second, we're going to print the shape of x. What happens to the x? Okay, so let's do it like this. So we're going to say d is equals to decoder block, and we have input 3. Okay, here we need skip connection, so let me change this input again, copy it and paste it here. So here let's say we have number of 64, and here we have 256 and 256. So it's a feature map of number of channels 64 and height and width like 256 by 256. Okay, so number of input channel would be 64. Let's say number of output channel would become 32. Okay, so we're gonna give as it as inputs, and next we need skip connection. So if skip connection should be, okay, I'll tell you skip connection. So let me just remove it for now. Here we'll include it, but I don't want to create any confusion. That's why I'm removing it right now. Okay, so you can see first shape is the here the input, and second is the output of the transpose convolution. So we're going to see what happened. So you can see the origin shape is 2 by 64 by 256 by 256. So here in the next, the output of the transpose convolution, the batch size remains the same. It always remains the same. It won't change in the entire network, but the number of channel reduces by half. This is a 32. We have specified manually as a 32. So here you can see the height and width doubles. It became from 256 to 512. So that's the change occur. Now let's go to the rest part of the paper. So you can see every step of in the expensive path consists of upsampling, feature map followed by 2 by 2 convolution that halves the number of feature channel. Okay, we have done this 2 by 2 convolution, and we have half the number of feature channel. Next, a concatenation with a correspondingly cropped feature map from the contrasting path. Next is a concatenation between the output of the this transpose convolution and the skip connection. So we're going to add skip connection here. So you can see in the paper it's mentioned that a cropped, you can see cropped feature map. Cropped basically means, because if you're going to use unpadded convolution, then the size would differ, so you need to crop a little bit. But as we have used the padded convolution, so we don't need any cropping, we just need to check the size. So okay, we have the size of the x, the output of the convolution block, output of the transpose convolution. Now we need to check the shape of the skip connection. We are going to specify the skip connection here. So skip connection should be of the size 512 by 512. The number of channel can differ. So we're going to say torch dot random n 2 by 32, let's say 512 by 512. Okay, and we're going to say skip here. Okay, so let's run it for now. Okay, so you can see both the height and width are same. Number of channel can differ, or anything can be done with them. So next we need to have a concatenation operation. So we're going to say torch dot cat, and here we have x and the skip. So one thing we also need to know on what axis we are going to concatenate. Okay, so axis would be 2. We are going to concatenate number of channels. Okay, that is 1. If you're going to say the first is 0 and this is 1, so on the axis 1. Okay, so done. Now we are going to print the shape and see. Okay, the shape became 64 by 512 by 500. Okay, that's good. Now it is followed by the we're going to say the convolution block. Okay, let's see the next. Okay, here we have the correspondingly cropped feature map from the encoding path. So this is skip connection concatenation. Next, and 2 3 by 3 convolution, each followed by ReLU. So again the convolution is, the cropping is necessary due to the loss of border pixel in every convolution. Okay, as we've told, because they use unpadded convolution and we are using padded, so that's the reason in this paper the cropping is necessary, but here we don't need cropping. Okay, now next follows the convolution block. So we're going to say self.conv. Here one thing is important, the number of output channels in this here is 64. So basically means 32 plus 32. Okay, so the number of output channel for up is, like we can say, so let me first write this. So here we need the number of input channels. Okay, for this, how many number of channels it have, we're gonna systematically do it. So first it add this, okay, this layer. So it has output C, so we're gonna say output C plus, then we have skip connection. So skip connection, I'm gonna tell you how, because currently we are using like 32. Okay, and 32 is also the out C. So we're gonna say out C, and then we need the output in the same shape only, output C channels. Okay, I hope we are not confused here. If when we are going to build a complete network, again I'm going to explain this thing. So let's don't worry if you haven't understood, don't worry, we're gonna do it again. X, and we're going to return X. Okay, so we have the decoder block ready. We're gonna print X dot shape. Okay, so you can see 32 by 512 by 512. Okay, so we have both the encoder block and the decoder block ready here. Now we need to build the entire architecture. So let's start building it again in class. Let's call it build unit. I hope you have watched my other video on TensorFlow also. I basically made more video on TensorFlow because I started with machine learning and deep learning with TensorFlow, so that's why. If you are more into PyTorch, don't worry, I will release more videos on PyTorch also, but you can check those videos also, they are not that bad, you can get some information from them. So let's continue with our code. So this is the constructor. First is self. Okay, we don't need anything from here, this constructor. Next is super. Okay, so first we're gonna write the number of encoders. We need 4 encoder blocks, so let's call them E1, E2, E3, E4. Okay, E1 equals to encoder block. So let me just copy this template. So here the number of input would be 3 as we are working with the RGB image. But in this video we are not going to do any training would be maybe next video. We're going to use this unit and train it on any data set. Okay, so number of input channel would be 3 and number of output would be 64. Then the second encoder block, let's call it E2. So its output would be, okay, its input number of channel would be the output number of channel of the encoder one, that is 64, and it's double, okay, after every encoder block. So like this, we're gonna E3, number of input channel 128, number of output channel 128 into 2, that is 256. And the last decoder block, not the decoder, the encoder block, input 256 and output 512. Okay, so we have a bottleneck block in between. If you go to the diagram, so you can see here we have these convolution block also in between the encoder and the decoder, where no skip connection basically is there. So it's going to be, let's call it bottleneck, because it's like a thin, like the neck of a bottle. So we're gonna say self dot b, okay, and self dot b equals to con block, and number of input channel 512, number of output 1024. So let's run it till, so let's build it till now and check, because maybe we have some issue, we run into some issue. So first of all, let's run this. Okay, so we have inputs, and then okay, so the encoder give output as skip connection. First the output of the convolution block that act as skip connection, and the pulling output of the pulling layer. So we're gonna call S1 P1 equals to self dot E1. So let me copy this line. So here we need inputs as inputs. Second we can call it S2 and P2. So that's how the numbering changes. And the input for the second encoder block put the output of the first encoder block, that is the output of the pulling layer. So we're gonna call P1 here. Let me copy it. And we have S3, P3, and input would be P2. And last we have this okay, I haven't renamed these, D3 and D4. Okay, we have S4 skip connection 4 and pooling layer 4. So so the input for the encoder, fourth encoder would be the output of the third pooling layer. Okay, till now it is done. Let's do one thing. Let's print some like S1 dot shape, P1 dot shape. Okay, let's print everything from above, all the outputs. So we're going to rename them S2, S3, S4, and same for the pulling block S2, S3, S4. And we're going to call it here inputs source dot rand n 3 500. Okay, should be, there should be batch size. Let's call it 2, height 512, width 512. So here first row is the skip connection shape and second is the pulling shape. Our major task is to just remember the skip connection, because they're going to be added to the decoder and we need to add them appropriately. Okay, I haven't called the build unit. Okay, build unit and inputs. Okay, there's some issue. Okay, so what's the issue here is okay, self inputs. Okay, let me just check it again. So it's like build input takes one positional arguments. Okay, we have init, call it, then we have self. Okay, then we have super init. So what the issue? I'm not getting what the issue here. Forward self inputs. Okay, so what's the mistake here? I'm not getting, or they are not aligned. They're aligned. Yeah, they're aligned. Okay, let's just need to check what the issue is again. Let's just run it again and see. Okay, we have same issue. What's the issue? This is okay. Just I'll pause the video and check it and then tell you what the error is. Okay, I know what the error is because it's not like this. My mistake. I've done it incorrectly. So we're gonna call it the model, and inside model we need to give the input. The inputs, that is the tensor, and then we need to run it. Okay, so you can see the shape for the skip connection and the shape for the pooling block. Okay, so these are important. Just remember, it starts with the 512 at the beginning and then gradually decreases 256, 128 and then 64, and the output of the last block, the last pooling layer is 32 by 32. Okay, so let's continue. So if you reach this still part of this video, I'm sure that you are enjoying this. So please click that thumbs up to like the video, and more, this basically motivates me to build more videos, and also subscribe the channel for more such videos. Okay, so now let's continue with this bottleneck part. So we're gonna remove this these print statement from here. So we're gonna say b equals to self dot b, and here input would be p4 because it's a convolution block, so height and width would remain the same. So b output of b would be 32 by 32, basically the height and width shape. Now we need the decoder blocks. Okay, so we're gonna say start with d1, say decoder block. So there would be 4 decoder block. They start with 1024, and the number of filter would gradually become half. So that's how we're gonna write second decoder. Input number channel 512, output would be 256. Same with the d3, input channel 256, output 128. d4 would be 128 and the output channel would be 64. So okay, so decoder block is done. Now we need to call it in the forward class. So we're going to say d1 equals to self dot d1, and it need two input. First is the b and second is skip connection. So b's shape like is b is of shape 32 by 32, so let's call it 32. It's gonna go through the transpose convolution and become 64. Okay, it doubles, and you can see from this console the last skip connection has the size 64 by 64. So this means s4 has the size 64. So we're gonna say s4 here. Let me remove this from here. Okay, so this is done. Now we're going to go to the decoder block again. So a d1 takes basically 1024 and 512 as the input, and what do we see? The output for the s4, basically this encoder flow 4 block would be 512. So understand this please carefully. So we have the input number of input channel for the that is d1 block start with 104, and the output channel would be 512. Okay, so this input passes through the transpose convolution here. It passes through transpose convolution block, and number of output channels became 512. Okay, now we have the skip connection which is s4. Okay, s4 basically means e4, so it also has number of output channels as 512. So we basically need, now here the concatenation occur. So number of channels are like out c plus out c. So that's why we have added this here. Just the thing is that you need to manage the shape, or you can use them manually. You can write them manually. It's not an issue. Just that you need to just check the shape and get a little bit understanding, and then it would work perfectly. So okay, like this we're gonna do the rest of the decoder block. Here d2, and the input for the d2 would be the output of d1. So we're gonna say d1, and skip connection would became s3, like it would go sequentially. Again we're gonna copy, change them to from d2 to d3 and d2 and s2, again d4 d1 d2 and it's d3, skip connection s1. Okay, so we have reached at the last decoder block. So let's print the shape. and check it. Okay, okay, it's taking time, so this means that I hope it's processing. Okay, it's processing. So you can see we have reached a size, a height and width of 512 by 512. So here we have written to the original shape. Okay, you can see original input shape is like 512 by 512, and here the last decoder shape is 512 by 512. Now let's continue with the paper. Okay, so we have the cropping is necessary due to the loss of border pixels in every convolution. Okay, this is done. At the final layer, a 1 by 1 convolution is used to map each of the 64 component feature vector to the desired number of classes. In total, the network has 23 convolution layers. Okay, so we need to at last we need to use a 1 by 1 convolution with a number of classes as the channels. Okay, so we're gonna say outputs, or let me give a comment here. Okay, what I've done should be like classify. So this is how it is. Outputs is like nn dot con to 2d number of channel. It's up to you how many classes you have, but the input would be 64 and output is up to you. Like if you are doing a binary segmentation, it would be 1. If you are doing multi-class like 10 classes, you can type 10 here. If you have 3 classes, type 3. So let's assume we have 1 class and kernel size would be 1. And if kernel size is 1, make sure the padding is always 0. Okay, padding would not be 1, otherwise it was code an issue. So we're going to say outputs equals to self dot outputs, and we're going to input d4 here and return outputs. Okay, so this is the architecture is done now. We just have to see y. So I'm going to print y here, the shape of y. The shape is really important. Okay, it's processing as it's taking time. So you can see batch size remains always the same 2. Now the number of feature channel, the number of output channel are 1, and the shape is 512 by 512. So we can say we have a shape of like, we have given a shape like 512 by 512 with number of channel 3. It has gone through the entire architecture, the encoder, the decoder, and then connected with the skip connection and all these things, the output layer, the last classifier layer, and then output is like we are getting a 1 channel of the same shape. So basically this 1 channel is basically denote the mask. Okay, in case of binary. Okay, so that's the entire thing about the unit architecture. So I hope you get some new information from this tutorial and this video. And if you get some new information, make sure that you like the video, subscribe the channel, and if you still have any issue or any query, then comment below, or you can check my social media and message me there also. And I hope you would share this video. Thank you and have a nice day. Do check the description for other links. Thank you.